Today we'll discuss about electromagnetic induction and the AC generator or alternating current generator. First, what is electromagnetic induction? As we discussed this topic earlier, that whenever there is a change in the magnetic field, that will produce EMF. So example, you have a wire, you place a wire which is between the two magnetic poles, and you start to move this wire. You are moving it downward. So when a wire is moved across the magnetic field, as you can see in this figure, what it will produce? It will produce a change in the magnetic field. And according to electromagnetic induction, whenever there is a change in the magnetic field, the EMF will induce. So it is the production of EMF or voltage in a conductor when there is a change in the magnetic flux linkage. What is the meaning of magnetic flux linkage? The term magnetic flux linkage means how many field lines are passing through unit area. For example, it is similar to that of magnetic field. You have a magnet placed next to another magnet, opposite poles are facing each other. The direction of the magnetic field is from north to south. So what is the meaning of magnetic flux linkage? Magnetic flux linkage means number of field lines The term magnetic flux linkage means number of field lines passing through So the term magnetic flux linkage means how many field lines are passing through unit area. That is called magnetic flux linkage. So if we move this wire within the magnetic field, either move up or down, there is a change in the magnetic field, and whenever there is a change in magnetic field, what will happen? It will induce or it will produce EMF. How to find the direction of induced EMF? How we can know which direction there is an induced EMF? So for that purpose, we have to use a Fleming's right-hand rule. What is the Fleming's right-hand rule? Fleming's right-hand rule is similar to that of left-hand rule. In a left hand, the first finger represents the field. In right hand also, first finger represents the field. Second represent in which direction the current produced, and the thumb shows the movement of the wire, which direction the wire is moving. So example, if I want to apply a Fleming's right hand rule here to find the direction of induced current. So example, if we don't know the direction of induced current and we want to find which direction the current will produce or induce. So using a right hand rule, the first finger should point in the magnetic field. So your first finger or index finger should point towards right hand side. You can also apply this rule. Your first finger should point in the direction of the magnetic field, or index finger point in the direction of magnetic field. Your thumb represents the movement of the wire. This wire is going down, so the thumb is showing the motion of wire. If the wire is going down, so that is the movement of the wire. Now, where your second finger is pointing when you apply the right hand rule, first finger is pointing towards south, second represent thumb represent the movement of the wire. So so it is towards you or it is out. So what will happen means the direction of the current is out or the direction of the current will be in this manner. Is it clear? How applying a right hand rule, the same way we apply a rule, but this time to find the direction of induced current we call that as a right hand rule. The first finger, the index finger, you use a right hand rule. So using a right hand rule, first finger should point in the magnetic field south. So your first finger should point towards the south pole. Your second finger represent, uh, you don't know the current, so now you know the motion of the wire because the wire is going downward, moving downward. So your thumb should point downward. So when your thumb will point downward, which direction your second finger is pointing, the direction in which your second finger is pointing, that is the direction of the induced current. Is it clear to everyone? I'll give more example. So example, you have, so right hand or Fleming's right hand rule. It is used to find direction of current produced due to change in magnetic field. So the current produced due to change in magnetic field, we can use this Fleming's right hand rule. According to this rule, the first finger will point towards magnetic field south. The second finger will show a direction of the current, and the thumb will represent the motion of or movement of wire or the force on wire. So example, you have a magnet. North and south, and you place a wire. So a wire is placed and you're moving this wire up. Here, to find the direction of induced current or current produced due to change in magnetic field, we use right hand. If we know the current, if you have a battery and we know the magnetic field, to find the force we use the left hand. So that is the difference here. There is no supply, there is no battery. When you move the wire, there is an induced current, and for that purpose you will use the right hand. Example, you are moving it up. This is the motion of the wire. So if the question is draw an arrow to show the direction of current, which direction current will produce? Use the right hand rule. Your first finger should point towards south. In this example, it is towards right. Your thumb represent upward. So which direction the current will produce? So the current will be into or inside, or if you want to show the direction of the current, how we represent the direction of the current, so it will move in this manner. Is it clear? The first finger is pointing in the magnetic field, which is towards right hand side. The index finger, your thumb is representing the motion of the wire, which is upward, and the current will show the direction in which so the second finger represents the direction in which the current is induced. Same way, if we have your first finger should point in the direction of a magnetic field. The second finger shows the current and the thumb is representing the motion of the wire, which direction you are moving the wire. Example, you have north and south, and there is a wire, and you are moving this wire downward. This time the motion of a wire is downward. What will be the direction of induced current? So the direction of induced current will be out. The first finger point in the your first finger, index finger, should point on the right hand side. Your thumb should point downward. So when you apply the rule, your thumb is pointing down, first finger is representing the magnetic field. So the direction of the current, it will come out in this manner. Is it clear to everyone? Like, you should be able to apply a rule and find the direction of the induced current. According to right hand rule, you have to use, keep in mind, you have, for finding the direction of induced current, you should use the right hand. Your first finger, your index finger should point in the direction of the south. So your first finger or index finger should point in the direction of the south. As you can see, the south is on the right hand side, so my index finger is pointing towards right hand side. The thumb should point in the direction of the motion of the wire, so my thumb should point downward. So index finger is pointing towards south, my thumb is pointing downward. Where the finger is pointing out of the screen. So when I draw the direction of the current will be outward. Is it clear? So the three rules are there in magnetism. So what are the three rules in magnetism? You have right hand grip rule, you have Fleming's left hand rule, and you have Fleming's right hand rule. Now, what condition you are using these rules? What is the purpose of a right hand grip rule? It is used to find direction of magnetic field due to current. And this rule is further divided into two categories. One is for a straight wire and the other one is for a circular wire or a solenoid. For a straight wire, your thumb will represent the current and the fingers will show magnetic field. But for a solenoid, it will be opposite. The fingers will show the current and the thumb will represent the north pole of a magnetic field. And just a simple example, like if you have a wire which is carrying the current into. So if this wire is carrying current into and I want to show the direction of this wire is carrying current into and I want to show the direction of magnetic field. So I will use the right hand grip rule. My thumb should point into the screen and fingers will turn around. So as I catch the wire, the direction in which the fingers will turn, that is the direction of magnetic field. So magnetic field lines will be around it. And when we show or represent, we represent in this manner. And it can be other way around. I'm just giving one example for each so that you can have a better understanding of these rules. If we have a solenoid means circular wire. So example, you have a cylinder on which you wrap the wire around, turn the wire, and you are passing the current. The big line is representing a positive terminal, small line represent negative. So direction of the conventional current is from positive to negative. Now, how we will apply a rule here? In this example, we'll use a Fleming right hand grip rule. Our fingers will turn, my fingers will turn in the direction of the current. As I grip the wire, my thumb will point towards the north pole. So in this example, the north pole will be on the right hand side. So on the right hand side, I will have a north pole and on the left hand side, I will have a south pole. And the magnetic field lines, because there is a magnetic field, so magnetic field will be around from north to south and within the wire it will be straight. This is what we did when we use a right hand grip rule. What is the Fleming's left hand rule? Fleming's left hand rule, it is used to find force on the wire which is carrying current. In magnetic field. And in this rule, the first finger for a solenoid, the fingers will turn in the direction of the current as the current is going down. So my fingers should point as I grip the wire, like if this is a circular wire or a solenoid. So this is a circular wire or solenoid. The current is going around it, as you can see. So when I grip this wire in the direction of the current, the thumb will point in the direction of the north. So in this example, my thumb is pointing on the right hand side for me So that's why north is on the right hand side and south will be on the left hand side. And for Fleming's left hand rule, the first finger represent magnetic field south. The second finger, you have to learn these rules, represent direction of the current, and the thumb will represent the force. So example, if you have a wire which is carrying the current in a magnetic field, so you have a north pole, south pole, and there is a current passing in the through the wire which is placed in a magnetic field. So if I want to find the direction of the force on this wire, first thing, because I know the current is downward, I want to find the direction. So if I want to find the direction of the magnetic field, first finger, if I want to find the direction of the force, the first finger represent the magnetic field which is towards the right hand side or south. The second is representing a direction of the current is pointing downward, and where thumb is pointing, that is the direction of the force. So in this example, when you apply a left hand rule, the first finger, index finger, is pointing towards south, the second is representing a direction of the current, and thumb is pointing out. So what will be the direction of the force in this way? One, the force will be outward. Is it clear, the direction of the force? And the last one, Fleming's right hand rule. Where we use this right hand rule, it is used to find direction of current produced due to change in magnetic field because of movement of wire. So the same rule is there, but to find the direction of current produced due to a change in magnetic field, we will use a right hand rule. So we have north and south, and example, the wire is there. We don't know because we are finding the direction of induced current. Example, the wire is there and you are moving this wire either upward or downward. Example, we are moving it up. So that is the motion of the wire. If you want to find the direction in which the induced EMF is there or direction in which the current produced, what we will do, we will use right hand rule, Fleming's right hand rule. The first finger point in the direction of the magnetic field. So magnetic field is pointing on the right hand side. So first finger, south is pointing towards right. So first finger is pointing towards right. The thumb represents the motion of the wire, the movement of the wire. So thumb is pointing up because this wire is moving up. The current, the finger represents the current. So the second finger is pointing into. So when we show the direction of the current for this wire, it will carry a current into. Is it clear? The three rules in magnetism: the right hand grip rule, the Fleming's left hand rule, and the Fleming's right hand rule. The last one, your first finger point towards south, use the right hand. First finger point towards south, the south is towards right. The thumb represent the motion of the wire because this wire is moving up. So motion of the wire is upward. The second finger shows the direction of the current because the second finger is pointing into. So the current will move inwards, and the inward direction according to the question is this way. So this is a right hand grip rule, right hand rule basically, not the grip one. So what happens if we change the, if magnetic field is changed, the direction of induced current will change. The factors which can affect the induced EMF or the EMF produced due to change in magnetic field. If we move the wire faster, it will produce a greater change in magnetic field or magnetic flux linkage, so higher induced EMF. If you use a stronger magnet, it will produce higher EMF. And if you use a longer wire, it will also produce a greater or higher induced EMF. Now AC generator, alternating current generator or normal generator, they based on the electromagnetic principle of electromagnetic induction. What is the principle of electromagnetic induction? It states that whenever there is a change in magnetic field, there is induced EMF. So example, you have a simple AC generator. You have to learn this label of AC generator. Now what and how it produces electricity. You have a rectangular coil, you have the carbon brushes, slip rings. What will happen as we rotate this rectangular coil? There is a change in the magnetic field, and when there is a change in magnetic field, there is a EMF, voltage or current produced. That's why this lamp will light up. So simple working of AC generator, what happened, how it works. Example, you have, these are the magnetic poles. You have a rectangular coil. Example, you are looking from the sideways, so this is how the rectangular coil will appear. Initially it is exactly vertical. Now as you rotate this Initially it is vertical, we start with a vertical. Now what happened when we start to rotate this, the new position, I'm representing the new position with a blue color. So this is the new position of this rectangular wire. What is the change in the angle as it rotated from position 1 to position 2? What is the change in the angle? First it is exactly vertical, then it becomes horizontal. So the change in the angle is 90 degrees. Now what happened, as you can see, when the wire rotate, as the wire rotate, there is a change in the magnetic field. And what happened to the strength of magnetic field? Which position strength of magnetic field is stronger? At position 1 when the wire is exactly vertical, or when the wire is exactly horizontal? When it is exactly horizontal, it is closer to the poles as compared to when it is vertical. So which condition we have a stronger magnetic field? When it is horizontal or vertical? When it is horizontal, we have a strong, because when it is exactly horizontal, it is closer to the poles as compared to when it is vertical. So what happened when we move the wire from horizontal position, yeah, second position, it is a stronger magnetic field. So when we move the wire from first position to the second position, there will be an induced EMF because there is a change in magnetic field. And what happened to the strength of induced EMF? It will increase. So this is position 1 and this one is position 2. Now from position 2, it is at position 2, it moved from position 2 to position 3. So this one is position 2 and this is position 3. What happened to the strength of magnetic field moving from 2 to 3? Will it increase or decrease? So the strength of magnetic field will decrease, or induced EMF will also decrease. So moving from position 2 to position 3, the induced EMF will decrease, or the change in the magnetic field will decrease. Then moving from position 3, so it is at position 3 and it moved from position 3 to position 4. So this is 3 and this one is 4. What happened to strength of magnetic field moving from 3 to 4? So again it will increase, but this time, look, if I first, this example, this side, if I say this is A, end A, this end A was moving close to south. Now this end A is moving close to north. So when this end A is moving closer to north, the induced EMF will increase, but in opposite direction, because according to Lenz's law, the direction of induced EMF depends on direction of the change in magnetic field. So current will increase, but in opposite direction. So this one is position 4. And from position 4, it will again become, so from position 4, it will return to position 5. So moving from position 4 to position 5, what happened to strength of magnetic field? It will decrease in opposite direction. So what happened? It will decrease here and this will be 5. So this is the one complete cycle of AC generator. First what happened? This is the change in angle from 0 to 90. Then this is from 90 to 180. Yes, I will repeat, 180 to 270. And this is from 270 to 360. Look, the last two, what happened? If we say this coil was having side A and this is side B. So when we were moving, rotating, first side A was moving closer to south. But now what happened? When it is rotating, the side A is moving closer to north. So it is moving in opposite pole. Whenever a wire or a movement of a wire is changed or the pole is changed, direction of induced current will also change. So this is showing one direction of the current, a positive, and the negative cycle. This is showing the negative or opposite direction of the current. So that's why we call that as AC generator produce alternating current, because the direction of the current is not same. It changes in one complete rotation of AC generator. It is changing from one way to another. And when you have a zero voltage, like at position 1, position 3 and position 5, so it means the coil is vertical. And when you have a maximum voltage, it means the coil is horizontal. So horizontal positions, maximum voltage will be there, and vertical positions, minimum voltage will be there. Why the graph is curved, not a straight line? Because this is not a linear change. This is not a constant change. How it changes, like how the magnetic fields are changing from one end to another. So it's a non-linear change in magnetic field. Like example, if the magnetic field is 0, then it becomes 20, then it becomes 30, then it becomes 45. So the change is not constant in the magnetic field. That is why it is a non-linear. And why the graph fall down, or the direction of induced current changes? As you can see, the graph of voltage output against the time for AC generator. You can see here, first you have a rectangular coil which is exactly vertical. When it rotated when it rotated 90-degree, the induced EMF is maximum. At this position it is horizontal. When it again become vertical, the induced EMF, the change in magnetic field decreases. That's why the induced EMF decrease. So when it is at a vertical position, voltage will be 0. When again it is horizontal, but what happened, like example, if this was side A and B first, but now the side changes. So when the side changes, the sides which are facing the magnetic pole changes, the direction of induced current will also change. So if this was producing a higher positive voltage, this will produce a negative voltage or negative current. Means the current will produce but in opposite direction. And again it is vertical. So when again it is vertical, so this is one complete cycle. One complete cycle produce one wave of a AC. Then again it continue to rotate. Again it will be horizontal, then vertical, then horizontal, and then vertical. So that is a second turn, and it will so on or goes on. Is it clear about the AC generator, alternating current generator, how it produces electricity? The basic idea, basic principle is that when the rectangular coil rotates in a magnetic field, there is a change in the magnetic field, and due to the change in magnetic field, there is induced EMF.